Having looked at the expression for pressure, which is given as P equal to P 0 plus rho g h, this being the atmospheric pressure as we have discussed, and this is the pressure due to the liquid column of height h. We now want to do some problems using this formula, that is pressure due to liquids, which is given by this. So, let us do a problem which says that the surface of water in a storage tank is 20 meter above the water tap in the kitchen of a house. So, this is understandable that there is a storage, overhead storage, water storage tank which is there on the terrace, and the distance where the kitchen is or the kitchen tap is, the storage tank is located 20 meters above the kitchen tap. So, the question is calculate the pressure at the tap, and of course, given that density of water equal to 1 into 10 cube kg per meter cube. This density is denoted by a quantity called as rho, which almost looks like P, but please do not distinguish this from P. It is called rho, R H O. So, this is equal to rho of water. So, now the pressure at the surface of the tank, that is at the surface of water inside the tank. So, there is atmospheric pressure, and the same atmospheric pressure also is there at when the water is issuing out from the tap. So, essentially the pressure difference is simply given by so delta P is the pressure difference, which is simply given by rho g into H, where rho is of that of water. So, this is equal to 1 into 10 cube kg per meter cube. G is 9.8 meter per second square, and H here is 20 meters. So, if you do this, it becomes 1.96 into 10 to the power 5 Newton per meter square, which is also called as 1.96 into 10 to the power 5 pascals. So, this is the pressure difference that is there at the between the surface of the water level inside the tank to the tap, the nozzle of the tap from which water issues out. So, this is a simple plug-in type of example. Let us do another one. Again a plug-in type, however, it is related to human body again. So, what is the difference in blood pressure between the top of the head and the bottom of the feet of a 1.60 meter tall person standing vertically. So there is a person who is 1.60 meters tall, and you are needed to find the pressure, the blood pressure, the difference in the blood pressure between the top of his head from the bottom of his feet. And the person is assumably standing vertically. Now, the input that needs to be given in this case is the density of blood and just keep in mind that this density of blood that I am going to give you is actually the average density of blood, because the blood consists of the blood plasma, which has a little less density as compared to the other cells that make up for the blood, which has a little more density. So, this is the average density of blood, which is 1060 kg per meter cube. Just take a note that this value for water is 1000 kg per meter cube. So, blood is a little more dense than water. So, again the pressure difference is given by delta P, it is equal to rho G H. Rho for blood is given as 1060 kg per meter cube, with a G to be 9.8 meter per second square multiplied by 1.60 meter, and this comes out as 16620.8 Newton per meter square. Okay, so this is the blood pressure difference between the top of his head to the bottom of his feet. So, let us do another problem. And the problem concerns, which all of you might have felt at times, that you have either traveled up through a hill and or traveled down very quickly, descended from a hill very quickly, or it might have happened when you have traveled in an airplane. Inside the airplane, the pressure is pretty much taken care of, but still one feels uncomfortable at times because there is a pressure buildup in the ears. And what happens is that there is a pop in the ear, which means that some air is released to equalize the pressure between the inner part of the eardrum to the outer part of the eardrum. And this, as I told you, that this can also happen if you are climbing a hill or you are getting down from a hill very quickly, and this can cause this popping of the air, as it says. So, if it does not pop, then there is a pressure that builds up, or rather there is a force that is developed, and that is why the ear starts aching. So, the question is what is the, so when you, not what is, when you run up a tall hill or run down the hill quickly, the ears pop. And as I told, pop means that some air is released from the ears, and this is due to the buildup of the pressure, due to that that the body takes a little while to get accustomed to. Suppose you are climbing down a hill very quickly, or you are running down a hill very quickly. So, the pressure difference that you initially had, and after you have gotten down quite a few say 1000 feet quickly. So, then this pressure buildup can happen. The question is, suppose this did not happen, what would be the force on the eardrum of area 0.5 centimeter square if a change in altitude, which means height, altitude, or you can just simply write it as height, of 1000 meter takes place. So, if there is a height difference of 1000 meter that takes place, and if the ears do not pop, so what is the pressure developed, and because of that pressure developed, what is the force that is exerted on the eardrum. So, again P equal to the pressure is equal to H, rho and G. Now, it has to be given that the rho of air, that is the density of air, it is 1.29 kg per meter cube. So, 1000 meter multiplied by 1.29 kg per meter cube multiplied by 9.8 meters per second square, and this thing when you calculate it, it comes out to be 12642 Newton per meter square. So, this is the pressure that is developed between the inner part and the outer part of the eardrum. Because of this pressure, there is going to be a force which is equal to the pressure multiplied by the area, which is 12642 Newton per meter square, and you multiply it by 0.5 into 10 to the power minus 4 meters square. So, the meter square will cancel and this becomes equal to 6.32 Newton. So, this 6.32 Newton is a force that is exerted on the ear. Now, you can take this as suppose, just for the argument's sake or making matters simple, let us take G equal to 10 for now, and which means that there is a weight of 0.6 kg that is exerted on the ears. And this is most of the times this is not an unbearable situation, but however, you would find actually children crying inside the airplane, and the reason more often than not is going to be because of this pressure that develops, and that creates an ache and the child cries. So, we have looked at mainly so far the density of liquids. We have defined density, and we have also looked at density of solids, liquids and gases, and we saw that the density of gases is at least something like 3 orders of magnitude less than that of the other solids and liquids. And we have also learned about specific gravity, and also we looked at the pressure that is exerted by a liquid column of height h, or the pressure that is felt at a point inside the liquid at a depth h from the surface, and used that result to compute some simple problems so far. We have talked about the pressure due to liquids inside a container which is full of liquid, and then we have calculated what is the force at a depth h from the surface. Now, let us look at the pressure due to air or our atmosphere. So, we will talk about the atmospheric pressure. However, atmospheric pressure has a large variation with the height measured, say, from the surface of the earth. And so, it is not like really like liquids, where the pressure really does not, or rather the density does not change much. Here, of course, the density will change a lot, given the fact that air is significantly compressible. So, it is done in the spirit of a problem. I think this is a better way of doing this problem. So, we will write down the problem, and then it is not a numerical problem, it is only a problem of finding the pressure in the Earth's atmosphere as a function of the height measured from the sea level. Okay. So, determine the variation in pressure in the Earth's atmosphere as a function of the height y above sea level assuming G to be constant. Constant means constant over the distance that we are considering. So, over a height h measured from the sea level. So, G is not varying, and that the density of air is proportional to pressure. So, we need to know the variation of pressure as a function of the height being measured from the sea level. There is an additional part to this problem which says also at what elevation is the air pressure equal to half the pressure at sea level. And the atmospheric pressure, let us just call it as P atmospheric or ATM, it is equal to 1.013 into 10 to the power 5 Newton per meter square, same as Pascal. So, we have the first part is about deriving an expression for P as a function of y, and the second part is that at what y or what height the pressure is equal to half of the atmospheric pressure. The atmospheric pressure is given there. Okay. So, the clue is given in this part that the density of air is proportional to pressure. This you would learn in a different context, we will not go into that. We will take this data and write that rho by rho 0, which is equal to P by P 0. So, this P atmosphere will often be written as P 0. So, that is the standard atmospheric pressure. So, we will write it as P 0. So, rho is the density at the height that we intend to find, rho 0 is the density at the sea level, P 0 is the pressure at the sea level, and P is what we intend to find. So, we have learned earlier that dP dy equal to minus rho g. This is how the pressure varies with height and you can get that P as a function of y by solving this differential equation. This we have elaborately discussed earlier. So, now I am going to replace this rho by using this equation. Let us call this as equation 1 and let us call this as equation 2. So, I will put equation 1 rho from equation 1 and put it into 2. So, rho from equation 1 comes out to be P over P 0 into rho 0. So, that will give me, putting it in equation 2 is dP dy equal to minus P over P 0 multiplied by rho 0 and g. Let us call this as equation 3. Now, since I need to solve this equation, there is a dP here and a P here. So, let us take all the the pressures in one side. So, dP over P becomes equal to minus rho 0 g divided by P 0 and dy. Now, this equation should be the guiding equation to get P as a function of y. So, I can integrate it both sides in order to solve for P as a function of y. Now, in order to integrate, you need to put limits, and the limits are as follows, that let us take the y equal to 0 to be the sea level. So, this is the sea level, and where P equal to P 0. So, this is the atmospheric pressure. So, this is my the height is 0 at the sea level, and there the P equal to P 0, and at a general height y I want to find what is the pressure that is developed. So, I will integrate this from P 0 to P, so that the lower limit of dy goes to 0 and it goes up to y. So, remember that all these quantities are constants, where rho 0 is the density at the sea level, and if I solve this equation, rather evaluate the integral, it becomes log, because you see the dP over P is a log P. Now, putting the limits, upper lower limit and lower limit. So, log P by P 0 equal to minus rho 0 g by P 0 and y. So, this is the equation that we need to keep in mind. There is a negative sign there, which has the same meaning as we have discussed in the case of solids, that the P becomes, so P P decreases, so the atmospheric pressure decreases with increase in height, or the other way around, the atmospheric pressure increases as y is decreased. Now, this can be written in a little more compact fashion. So, let us erase this, but keep in mind that we have to calculate the second part, which is a numerical problem, where you need to find the height at which the pressure is half of that of the atmospheric pressure. So, this is equal to, so this is log of P minus log P 0, which is equal to or let us write this as, so I am skipping one step, and you can write it as exponential minus rho 0 g by P 0 and y. So, this is how the pressure varies with the height y measured from the sea level. So, the pressure, as I told you, that as I increase my height, the pressure decreases, and at y equal to 0, which is the sea level. So, if I put y equal to 0 here, P will become equal to P 0, and the decrease of pressure here is exponential. So, the pressure decreases exponentially at the height is increased starting from the sea level. So, let us do the numerical part of the problem, for which we need to calculate this constant as per the given problem. All these quantities are constant, and so rho 0, which is the density of water or density of air, I am so sorry, density of air at the sea level is 1.29 kg per meter cube multiplied by 9.8 meter per second square divided by P0, which is equal to 1.013 into 10 to the power 5 Newton per meter square, and this has a value 1.25 into 10 to the power minus 4, and this will have an unit of meter inverse or 1 over meter. So, that this y being measured in meters will cancel this, and your exponential will have to be the argument of the exponential will have to be dimensionless. So, in order to calculate where my p becomes P0 over 2, I need to find that y where my p becomes equal to P0 by 2. So, in order to find that, I simply take this equation and put P0 by 2 on the left hand side, which becomes P0, and exponential minus this quantity 1.25 into 10 to the power minus 4 meter inverse and y. So, this gives me I can take a log of both sides to calculate y. Y becomes log of 2, 1.25 and 10 to the power minus 4 meter inverse. Do you remember what is log 2 from your radioactivity classes? So, log 2 is equal to 0.693. So, this is equal to 0.693 divided by 1.25 into 10 to the power minus 4 meter. So, the meter will go up, and this becomes equal to 5550 meter. So, this is the height at which the pressure falls to half the atmospheric pressure, and sometimes it becomes important to know what is the this height expressed in feet, because sometimes especially in the mountains and tall hills are measured in feet. So, this is actually equal to 18,000 feet. So, at 18,000 feet, the pressure falls to half the atmospheric pressure. So, this is the reason that the mountaineers or the mountain climbers, they carry oxygen tanks along with them, because it is quite difficult to breathe at an altitude of 18,000 feet. So, let us discuss now two things. One is atmospheric pressure, which we have been discussing, and gauge pressure. We will tell you what gauge pressure is. So, the atmospheric pressure at the sea level, which we just called as P0, is equal to 1.013 into 10 to the power 5 Newton per meter square. In fact, there is another unit other than the Newton per meter square or the Pascal that we have talked about so far. There is another unit that is preferred more by the meteorological department, which is called as bar, and 1 bar. So, one bar equal to 1 into 10 to the power 5 Newton per meter square. So, in fact, the pressure, atmospheric pressure at the sea level is slightly more than a bar, the difference between 1 and 1.013. So, now you understand that this is quite a large pressure. Okay. The large pressure means if it corresponds to a force, which we know the relation between force and pressure. So, F is equal to P into A. So, if the pressure is this much, you know that the force is going to be also quite large. So, how does human body accepts or adjusts to this kind of pressure? And the answer is that all the living cells in our body gives an equal and opposite pressure, rather a pressure which is appropriate to adjust the pressure, that is enormous pressure that we have outside. So, there are pressures in the cells because of various things that are inside the cells. There is a cell pressure which adjusts with the pressure that is outside. You have seen a balloon which is given certain when you fill in air, it retains at least for some time, and this is so basically that filled in, because of the shape of the balloon, it retains the extra pressure, or rather it withstands the atmospheric pressure for some time, and over a period of time it kind of gets deflated. And same with the tires that we have in the cars and in other automobiles, that these cars are also given pressure, the filled in air, and because of this robust structure, it retains the air for quite a number of days, even when it is in running condition. So, how do we, so there is, you have seen that when you go to actually fill in air in your cycle tire or your motorcycle tire or the car tires, they measure it with a device which is called as a tire gauge. And this tire gauge measures the pressure that is there inside the tube, and it is actually specified that, suppose we talk about a vehicle, a car which is smaller car requires probably lesser pressure in its tires than a big truck needs much more pressure in its tire because it carries a lot of load. So, there is a specific amount of air that needs to be filled in. Anything more is not of course good, but anything less is also not good, because of the normal functioning of the vehicle would be affected if the tire pressures are continuously less than what is prescribed for them. So, the tire gauge is put in to measure the pressure of the tire. Remember, the tire gauge actually measures the pressure over and above the atmospheric pressure. So, what I mean to say is that, so a tire gauge measures a pressure P, which is equal to the atmospheric pressure and plus the gauge pressure. So, if a tire gauge measures the pressure of, if a tire gauge measures the pressure of 200 kilopascals. I keep shuttling between this Newton per meter square and pascals because they are same. Then the actual pressure is 200 kilopascal plus 100 kilopascal, which is this. I am taking this and this to be nearly same. The atmospheric pressure, I am taking it as loosely 1 into 10 to the power 5 Newton per meter square, or 1 into 10 to the power 5 Pascal. So, this is actually 300 kilopascal. So, the gauge, the tire gauge, the instrument that they put inside the nozzle of the tire to measure the tire pressure, will measure this. However, the actual pressure is 300 kilopascal, including the atmospheric pressure. So far we have seen what is pressure, or rather the pressure exerted by fluids, both for pressure of a liquid as well as pressure of air, and which what we also have defined is pressure due to the atmosphere, which is called as atmospheric pressure. Now, the question is how is pressure measured? There are many devices that are invented to measure pressure. We will only discuss only two of them here. One is a very simple device such as a U-tube. So, we are talking about measurement of pressure. So, this is a U-tube and it has a liquid that is present inside this. So, this is a liquid which is usually mercury, and so mercury is filled inside the U-tube, and this is where the pressure is measured. And let this pressure be P. So, we have P is equal to P 0 plus rho g h. So, the pressure that you measure here is related to the height difference of the fluid or of the liquid that is there inside the tube, and so we have discussed that there is a gauge pressure so this rho g h is called as a gauge pressure, and the total pressure is actually the atmospheric pressure plus the gauge pressure. So, this H is the height difference between the two hands of the U-tube, and this is the pressure that is measured here. P 0 is the atmospheric pressure, rho is the density of the liquid that is there inside, as we told that most of the times one uses mercury as a liquid inside. H is the height difference between the left and the right arm. In case the left arm has a level which is lower than that of the right arm, then the pressure that is measured here will be lower than the atmospheric pressure, and just as the case here, when you have this height to be positive, that is the left arm has more height than the right arm, then the pressure is said to be more than the atmospheric pressure, and there is a positive sign that exists between them. All right. So, this is how one measures pressure. This is one of the ways to measure pressure, and there are other ways, of course, we are coming to that in a while, but this gauge pressure or this rho g h factor is the important thing, and to know that to know the exact pressure, we just need to add the atmospheric pressure to the gauge pressure. So, at times, in fact, this product of rho g and h, that is density multiplied by the acceleration due to gravity divided by the multiplied by the height difference between them, between the two hands, is simply represented in terms of the height. So, when you say that so many millimeter of mercury we really mean that you have to multiply to get the exact pressure difference, you have to multiply the density of mercury. By the way, mercury is written with the symbol Hg. So, Hg is capital H small g, that is the symbol for mercury in the periodic table. So many millimeter of mercury means that the pressure difference will have to be represented. If you want the exact pressure difference, then you have to multiply it by the rho and the g with that many millimeter, so as to get the exact pressure either in Newton per meter square or Pascal or bar, whichever unit you want to express it in. Similarly, one can also use water. And you can also use water in place of mercury. The only simplicity that happens is that the density of water is known always, and it is simple to remember as well, and that is equal to 10 cube kg per meter cube, as opposed to mercury, which is more dense than that, which is 13.6 kg per meter cube. In any case, so there is a unit, it is called the mmHg. So 1 mmHg, mm is for millimeter, Hg is mercury. So 1 mmHg is equivalent to a pressure of, so this is 13.6 into 10 cube kg per meter cube, g to be 9.8 meter per second square, and 1 millimeter of mercury. So, we will take 1 millimeter, which is equal to 10 to the power minus 3 meter, and this is equal to 133 Newton per meter square. And this has a special name called as TORR, equal to 1 torr. So, this is after the name of a scientist called Evangelista Torricelli, who was there between 1608. So, E. Torricelli. 1608 to 1647. So, this is equal to 1 torr, which means it is equal to 1 millimeter of mercury. So, let us see that we have introduced many units of pressure. Let us see what are the differences between them, and also vis-a-vis the atmospheric pressure. We discuss different units of pressure. So, we have 1 atmospheric pressure, we will simply write it as 1 atm, means atmospheric pressure. It is equal to 1.013 into 10 to the power 5 Newton per meter square, which is equal to also equal to 1.013 into 10 to the power 5 pascals, which is equal to 101.3 kilopascals. Now, we have also introduced earlier another unit of pressure, which is used by the meteorological department to talk about the development of pressure or low pressure in areas adjoining the sea. while talking about the climates. So, there are says 1 bar which is equal to 1 into 10 to the power 5 Newton per meter square. So, if you see that the atmospheric pressure is slightly more than a bar, which is what we have mentioned earlier. So, this is equal to 1.013 bar, which is same as, we will see that in just a while, that it is equal to 76 centimeter of the mercury. Just as we told that 1 millimeter mercury. So, this is the 1 atmosphere is equal to 76 centimeter of mercury. So, the atmospheric pressure is same as the pressure that is exerted by a 76 centimeter high column of mercury, which is of course equal to 760 millimeter of mercury, and that is equal to, by just the definition that we have talked about, this is equal to 760 torr, which is equal to 1.03 into 10 to the power 4 millimeter of water at 4 degrees centigrade. So, it is 1 atmospheric pressure is not only can be represented in a column of mercury, but it can also be represented as a column of water. The water that the pressure that is exerted by water of this much of height, which is 1.03 into 10 to the power 4 millimeter. So, these are the interconversion of different units of pressure, and sometimes they are quite important. For example, we will give you the example of blood pressure. So, if you go to a doctor and the doctor measures your blood pressure, good blood pressure, which means healthy blood pressure, is 120 by 80, which is what they will tell you, and they simply write as 120 by 80 in the medical records that are specific to you, and they do not mention, most of the time they do not mention what it is, but it is actually 120. So, this is 120 and 80 are the ranges of blood pressure, and this is actually in millimeter of mercury. So, it is 120 millimeter of mercury for the higher one and 80 millimeter of mercury for the lower one. So, however, the atmospheric pressure is much more than the pressure that the blood exerts on the walls of the artery as the blood flows through the body. However, we have seen that because the living cells of the body exerts pressure in order to combat the pressure from outside, that is from the atmosphere, we maintain the shape that we are in and do not buckle to the pressure. Let us now talk about the second instrument by which pressure is measured, which is called as the barometer. And we are going to specifically talk about Mercury barometer. So, you take a tube like this full of mercury here. We have told that mercury is represented by Hg, and the density of mercury is equal to 13.6 into 10 cube kg per meter cube. So, it is actually quite a dense liquid. Now, if you invert this on a vessel containing mercury, then this is what is going to happen. So, I have taken a vessel which is completely full of mercury and invert it on this. So, which means that it will look like this. Okay. And what is going to happen is that there will be, so given that this tube is long enough, say something like a meter, then it is seen that the mercury is fills up to a certain level and there is a vacant portion on top of that where there is really a vacuum. So, P equal to 0 is a vacuum and the height of the liquid column stands at 76 centimeter. Okay. So, 76 centimeter of mercury, as we have said, is the atmospheric pressure. That is, in other words, a 76 centimeter column of mercury, 76 centimeter column of mercury exerts the same pressure as the atmospheric pressure. So, the pressure here is the same as the atmospheric pressure. When you have inverted this tube, the whole thing is, so there is the mercury is static, it's come to an equilibrium and there is a void that is created where there is a vacuum where the pressure is equal to 0, the height of the mercury inside the tube is at 76 centimeter. So, I repeat once more, a 76 centimeter column of mercury exerts the same pressure as the atmospheric pressure or 1 atmospheric pressure. So, 76 centimeter of mercury is said to be, as we said, that we will only quote the height. So, 76 centimeter of mercury equal to 1 atmospheric pressure. Now, suppose you want to fill it with water, not with mercury, and if it is with water which is H2O, which has a density of only 1 into 10 cube kg per meter cube, and in that case the height of the water column that you need is equal to, so height is equal to 10 to the power 10.3 meter. So, instead of 76 centimeter, if you use water, you need a height, the column of water should have a height 10.3 meter, which means it is a very long, it has to be a very long tube, and this much of that is 10.3 meter of water column exerts the same pressure as 1 atmospheric pressure. This has some implications in designing vacuum pumps. No matter what, however good a vacuum pump is, it cannot lift water to a height more than 10 meters because of this reason. And so, sucking out water or draining out water from a deep tube well which is more than 10 meter is a problem using vacuum pumps.